Exponential distribution. Exponential distribution is often used to model the length of time between the occurrence of two successive events, or the inter-arrival times. Examples of exponential distribution is related to the interval arrival times between two events. For example, the time between two successive trucks arriving at an unloading dock. The time between two successive transactions at an ATM machine. The time between two successive phone calls to the main operator. So as you see here, we are talking about inter-arrival time, or the time between two occurrence of two events. You can think of other examples. For example, the inter-arrival time between two messages that you get, or between two emails that you get, and things like that. Do you remember Poisson distribution? Poisson distribution is a discrete distribution. We use Poisson distribution when we are interested in the number of times that an event occurs, or the number of success, given an area of opportunity. The formula for computing the probability of X if it follows a Poisson distribution is as follows. Here, X is the number of success in a given area of opportunity. Lambda is the expected number, or the average number of success or event. E is the mathematical constant, and P of X is the probability that X number of events, or X number of successes, would occur considering the area of opportunity and given that we have lambda number of events or success. The reason we are reviewing this is because Poisson distribution and exponential distribution are related. If you consider the area of opportunity to be time, then Poisson distribution is the number of events happen during a period of time. So for example, x1 happens, if this is given, this is the time, t0 to t1, x1 could happen here, x2 could happen here, x3 could happen here, and etc. and etc. So Poisson distribution is the number of events that happen in this period of time. Exponential distribution is the time interval between two successes or two events. So this time interval between each events that happen during time follows exponential distribution, and the number of events that happens in a given time is Poisson distribution. This is how these two are related. Exponential distribution is defined by a single parameter, and that is its average or expected value, which is lambda. The probability density function for exponential distribution is as follows. Capital T here is the random variable, and it stands for time. So T here follows exponential distribution, and we show this by only one parameter, which is lambda. A small t is just the values that random variable t takes. So the probability density function of random variable t is equal to lambda, its expected value, multiplied by e to the power of negative lambda multiplied by t for any t greater than 0. The probability that the interval arrival time t is less than t is any given number is as follows. Probability that t is less than t is equal to 1 minus e to the power of negative lambda multiplied by t. Here e is the mathematical constant, approximately 2.71828. Lambda is the expected value, or the mean number of events per time unit, and t is any value of the continuous variable where t can be any positive value. Characteristics of exponential distribution. So we learned about the probability density function of exponential distribution, and that's f of t is equal to lambda multiplied by e to the power of negative lambda multiplied by t for any positive value of t. Here t represent time interval between two success, and it's a random variable that follows exponential distribution, and it's represented by parameter lambda. The probability function or formula for random variable t is as follows. The probability that t is less than any value t, so the capital T here is the random variable here, and the small t here is any value that random variable t takes. So that's equal to 1 minus e to the power of negative lambda t. We now can compute the probability that t is greater than or equal to t. And that is equal to, according to the formula, of the complement of an event. So this is equal to 1 minus the probability of its complement, which is t less than t. And if you replace this by this, you're going to get e to the power negative lambda t. So this is the probability. Let's now see the average and standard deviation of exponential distribution. The mean and standard deviation of exponential distribution, they are actually equal, and they are as follows. The average is 1 over lambda, and the standard deviation is also 1 over lambda. We can also now find the probability that random variable t is between two values, for example, t2 and t1. And that is equal to e to the power negative lambda multiplied by t1 minus e to the power lambda multiplied by t2. Remember that t2 here is the greater value and t1 is the smaller value. But when we write it, t1 is here and t2 is here. So the smaller value comes here first and then the bigger value. Let's see an example. Suppose customers arrive at a service counter at the rate of 15 customers per hour, which is equivalent to 1 customer every 4 minutes on average. How so? Right, so we have 15 customers per 1 hour. But 1 hour is 60 minutes. So if you divide 60 and 15 by 15, you get 60 divided by 15, which is 4, and 15 divided by 15, which is 1. So this means 1 customers per 4 minutes. Every 4 minutes, on average, you get 1 customer. What is the probability that the inter-arrival time between 2 customers is less than 3 minutes? So here we have a random variable t, which is the inter-arrival time between 2 customers. It follows the exponential distribution with a rate of 15 customers per hour, if you want to go with the scale of hour. In this type of question, you have to be careful to have the same scale for all your values. So for example, here we have the rate in hour based, and the question is asked for minutes based. So you either have to go everything in hour or go everything in minutes. Let's go everything in hour. If you want to go everything in hour, this means that this one also has to go in an hour. What is 3 minutes in hour scale? 3 minutes means actually every hour is 60 minutes. So 3 minutes is 1/20th of 1 hour. 1/20th of hour. Why so? Because an hour is 60 minutes. If you divide it by 20, you're going to get 3, right? So this means that 3 minutes is 1/20th of 1 hour. All right, so instead of 3 minutes, we're going to use t equal to 1/20th. So now our problem is easy. We are looking for the probability that t is less than 3 minutes, which is 1/20th of an hour, because our rate is an hour. And this is equal to 1 minus e to the power of negative lambda multiplied by t. Lambda here is 15 multiplied by t here is 1/20. which is both, if you do that, is equal to 1 minus e to the power negative 0.75. So the probability is equal to 0.5276, almost 53%. All right, we could also do this by scaling everything in minutes base. So this is in minutes. We have to convert this one also in minutes. So lambda here is 15 per hour, which means per hour, which is equal to one customer every 4 minutes, one customer per 4 minutes. But still we have to go to 1 minute. So this means that if we have one customer per 4 minutes, that means in each minute we're going to get 1/4 of a customer each minute. So lambda actually is 1/4. So this is our lambda in minutes. Now instead of this, which is in hour, we can go with in minutes. So that would be the probability that t is, by the way, t right now is follows the exponential distribution with lambda equal to 1/4 customers per 1 minute. So this is, we are looking for the probability that t is less than 3 minutes, right? 3 minutes. And that is equal to 1 minus e to the power negative lambda, which is 1/4, multiplied by t, which is 3. So again, this would be 1 minus e to the power negative 0.75, which is again the same as 0.5276.